Welcome back. In the previous lesson, we talked about the basic hardware of MRI. We also saw that the 90-degree RF pulse tips the net magnetization away from the B0 and create a transverse magnetization. Today, we're going to focus on what happened next, T1 and T2 relaxation. Question 1. What happened immediately after a 90-degree RF pulse? An ideal 90-degree RF pulse converts longitudinal magnetization into transverse magnetization. So Mx becomes close to 0 while Mxy becomes large. Because many spins initially rotate in phase, their transverse signal add together and produce a strong oscillating signal. As the spin gradually loses coherence, the signal envelope decays. The initial decaying signal is called the FID, or the free induction decay. Question 2. Is the FID a pure T2 signal? And what is the difference between T2 and T2 star? The first question is, not usually. The FID normally decays according to the T2 star, rather than the pure T2. This is because the spin loses transverse phase coherence for two different reasons. The first is true T2 relaxation. Right after the RF pulse, many spins are rotating in phase, and their transverse magnetic moment add together and produce a strong signal. Over time, microscopic spin interaction cause them to lose synchronization. As their phase spread out, the individual signal began to cancel, and the net transverse magnetization become weaker. This loss is largely irreversible. Different tissues have different T2 value because their molecular environment are different. Free water usually maintain phase coherence longer, and therefore have a long T2, while more tightly organized tissue tend to lose coherence faster and have a shorter T2. This is why fluid often appear bright on the T2 weighted image, while short T2 tissue appear darker. However, true T2 relaxation is not the only reason the FID decays. The second cause is magnetic field inhomogeneity. In the real MRI scan, B0 is not perfectly uniform. This local field difference may come from the scanner itself, but it can also be caused by differences in the tissue magnetic susceptibility, especially near air, bone, and metal. As a result, some spins experience slightly stronger or weaker magnetic fields and precess at different frequencies. Even without intrinsic T2 relaxations, this frequency difference would still cause the spin to spread out of phase. So the FID decays faster than it would from T2 relaxation alone. Simple way to think about the difference is to imagine runner moving around the circular track. Some runners spread apart because they interact with one another in unpredictable ways that represent true T2 relaxation. Other runners spread apart because they are running in length with slightly different speeds that represent static magnetic field inhomogeneity. The first type of phase loss cannot be fully reversed. The second type may be reversible, but the spins still follow a predictable frequency difference. This reversible component is exactly what the 180-degree RF pulse is designed to correct. Question 3. How does a 180-degree pulse create a spin echo, and does it reverse T2 decay? After a 90-degree pulse, faster spin move ahead while the slower spin falls behind. After a time interval, or tau, a 180-degree RF pulse flip their position in the transverse plane without changing their speed. The fast spin are now behind, while the slow spin are ahead. After another time interval of tau, spin rephase and produce a spin echo. The time from the initial 90-degree pulse to the peak of that echo is called the echo time. So the 180-degree pulse is usually applied halfway to the echo. However, the 180-degree pulse only reverses dephasing caused by the static field difference, such as the B0 inhomogeneity. It cannot reverse the true T2 relaxation from the microscopic spin interactions. This is why the echo is smaller than the original signal, and why the spin echo amplitude follows the T2 decay envelope. In contrast, the FID mainly reflects the T2 star decay. Question 4. Does every 180-degree RF pulse do the same thing? No. Its function depending on where it appears in the sequence. In the spin echo sequence, the 180-degree pulse is applied after a 90-degree excitation. Its purpose is to refocus reversible transverse dephasing and create a spin echo. It does not create T2 relaxation. Instead, it removes much of the extra T2 star dephasing, so the echo amplitude more closely reflects the true T2. In the inversion recovery sequence, a 180-degree pulse is applied first to flip the longitudinal magnetization from the positive B0 direction to the negative direction. Its purpose is to prepare the magnetization so the difference in the T1 recovery can be used to decrease tissue contrast or suppress specific tissue by choosing an appropriate inversion time. These two uses can also appear in the same sequence. For example, an inversion recovery spin echo sequence may use 100-degree pause for T1 preparation, followed later by another 100-degree pause for transverse refocusing. Question 5. What exactly is T1 relaxation? T1 relaxation is a gradual recovery of longitudinal magnetization back toward equilibrium along the B0 after an RF pulse. This recovery occurs because the excited spin gradually transfer energy to their surrounding molecular environment. For this reason, T1 is also known as the spin lattice relaxation, where the term lattice simply refers to the surrounding tissue rather than the rigid crystal lattice. Question 6. How does MRI measure T1? We wait for some longitudinal recovery to occur, then apply another RF pulse. Imagine that the first 90-degree pulse reduces Mx to nearly zero. During the following interval, Mx gradually recovers. At the chosen time, we apply another 90-degree pulse. This pulse rotates the recovered Mx into a transverse plane. The amount of the new MXY created depends on how much MX has recovered before that pulse. If only a small amount had recovered, the new signal is weak. If more MX had recovered, the signal is stronger. So the scanner is still detecting transverse signal, but the amplitude of that signal indirectly tells us how much longitudinal recovery has occurred. This means that the waiting time before the next excitation becomes very important, because it determines how much MX is available when the signal is measured. Question 7. What is saturation recovery, and how does TR create T1 contrast? Saturation recovery begins with a 90-degree RF pulse, which moves the longitudinal magnetization into a transverse plane and leaves the Mx close to zero. After the transverse signal decay, Mx gradually recovers toward positive M0. A short T1 tissue recovers quickly, while long T1 tissue recovers more slowly. TR, or repetition time, determines how long the tissue are allowed to recover before the next excitation pulse. With a short TR, the tissue are sampled before full recovery. The short T1 tissue have more Mx available and therefore produce a strong transverse signal after the next pulse, while the long T1 tissue produces a weaker signal. This difference creates T1 contrast. Saturation recovery starts from the Mx close to zero, but we can create an even larger separation between tissue recovery curve by first flip Mx to the opposite direction. This leads to the inversion recovery. Question 8. How does inversion recovery select a tissue, and how do Ti, Tr, and the Te shape the final image contrast? In reversion recovery, the sequence begins with a 180-degree preparation pulse. This flips the longitudinal magnetization from a positive M0 to a negative M0. The magnetization then recovers toward equilibrium, passes through the zeros, and eventually returns to the positive M0. Because the different tissues have a different T1 value, they cross zero at different times. If the excitation pulse is applied when a particular tissue has Mx close to zero, that tissue produces a very little transverse signal and is therefore suppressed, which is called the nulling. For example, TR used an appropriate TI to suppress fat, while FLAIR suppress CSF. After a target tissue is selected, TR controls how much longitudinal recovery occurs before the next excitation, while TE controls how much transverse decay occurs before the signal is measured. So TI is mainly used to select or suppress a tissue, while TR and TE shape where the final image appears more T1 weighted or T2 weighted. The simplest way to remember it is T2 is observed from the transverse signal decay. T1 is inferred from the longitudinal recovery after it is converted back into a transverse signal. Thank you for watching. I will see you next lesson.